Hello grade 11s, welcome back to the channel. In today's lesson we're going to be looking at electrostatic and we are doing grade 11 Coulomb's law. So without any further ado, let's just get right down to the lesson. So you will remember in grade 10 we said that we have two types of charges. We have a negative charge and a positive charge, right? So point number one is saying a charge is negative when it has an excess of electrons, meaning it has more electrons than protons. So if we had to indicate this one, let's say this is a charge, but then with this one we can see there we have our protons indicated by the positive, but then we have more electrons, right? So an excess of electrons. So all this charge will be what we'd say now we have a negatively charged particle or a negatively charged sphere, right? Then for case number 2, it says a charge is positive when it has a deficiency of electrons. So when we speak of deficiency, we say there are less electrons, right? Meaning there are more protons than the electrons. So in this case, we'd have this is a plus the protons, and let's say maybe we have 2 electrons like that. So we can see here there is a deficiency of electrons. The protons are more than the electrons, so we say this charge is this sphere is positively charged, right? Then we have an object or sphere is neutral when there is no charge, meaning it has equal number of protons and electrons. So now what happens if we have a sphere like this? So it has equal number of protons and electrons. So we say this one will have no charge, will be neutral, right? So this one will be neutral. Why? Because if we can count here, we have 4 protons and we have 4 electrons. That gives you 0, right? So that's neutral. That's a 0 charge. Awesome. Then they say when charges are brought together, they either attract or repel, right? So we know when charges are brought together, it's either they will attract or repel. What is to attract? To attract is to bring closer or bring towards the other sphere, and to repel is to move it away from a particular sphere. Then we say unlike charges will attract, that means they will move towards each other. And like charges will repel, that means they will move away from each other, right? So in other words, we're saying if you have a positively charged sphere and another positively charged sphere, because these ones are like charges, right? The charges are the same. What will happen? We expect them to move away from each other, right? So we say like charges, they repel. So again, if you have a negative charge and a negative charge, still these charges are the same, they're like charges, so they will move away from each other. That moving away, we call it repulsion, right? So they will repel. Now what happens if the charges are not the same? Let's say we have a positive, we have a negative. Now we expect them to attract, right? So they will move towards each other. So when the signs are not the same, or when the charges are not the same, they move towards each other. So you can have it this way or that way. So if the charges are not the same, they move towards each other. Unlike charges will attract, right? Then let's go on with the grade 10 revision. Again, we said when two spheres are made to come to contact, they share the electrons among themselves, right? Then the sphere or charge that has an excess of electrons share its electrons to the charge of sphere with a deficiency of electrons. So there's always a case whereby if here we have a charge that has excess electrons, right? Remember the electrons are the one that move the charges, right? Are the ones that move what can we call it, the electricity in the charges, right? So if we have an excess of electrons, the one with the excess of electrons will have to donate to the other one with the deficiency of electrons. Remember, the electrons, we say these are the charges that are able to move. Remember, with your protons are in the nuclei or on the nuclei of the atom, right? Meaning they cannot move, right? Remember, your protons and your neutrons, they cannot move, right? So collectively we know that your neutrons and your protons, they are known as nucleons, right? They are known as nucleons, and they are situated on the nucleus of the atom, and they cannot move. Then the only thing that is able to move are your electrons. So if you have it like that here, that is a representation. This is where you'd get your protons and your neutrons, and then on the spheres or on the orbits here, that's where you'd get your electrons, right? So your electrons are always orbiting here. That means they are the ones that are able to move. They're the ones that are able to move, right? So we say now when two spheres are made to come to contact, they will share those electrons among themselves, but then the way of sharing will be in the way that the one with excess electrons will give to the one with the deficiency of electrons. Now we say a sphere can either lose electrons or gain electrons, since it's only electrons that can move, right? The sphere with an excess of electrons loses its electrons to the sphere with a deficiency of electrons. We say the sphere with a deficiency of electrons will then gain, and then the electrons during contact from the sphere with an excess of electrons. So this is the case whereby we can make an analogy of a rich person giving to the poor, right? So in this case, the rich will lose his assets or money to the poor, then the poor in turn will gain, right? So we say the sphere with a deficiency of electrons will gain the electrons during contact from the sphere with an excess of electrons. However, the net charge of the electrons remain constant in an isolated system during any physical contact. So that is to say, initially the number of charges there will be conserved, right? So initially to finally the number of charges will be conserved, so no charges will be lost during that physical contact. So we say this principle is known as the principle of conservation of charge, which state that the net charge of the electrons will remain constant in an isolated system during any physical contact, right? So with this one, you will note that we have this case. So let's say we have a charge here, or a sphere of charge, -4 coulombs, and another sphere of charge +2 coulombs, right? So now what is happening with the principle of conservation of charge is that we want to bring these two spheres into contact, right? And just check in what way will they share the electrons, right? So this is how you do it. So you just take this one, so you will add the charges of the two spheres, and then divide by 2, because we are comparing the charges of two spheres, right? So now we have -4 plus 2, that gives us -2 divided by 2, that will give us -1 coulomb, right? So what is happening is when they now come into contact, they will share electrons, right? When they share electrons, they will come up with the same magnitude of charge, right? So now if we say this is charge A, this is sphere A, and this is sphere B, now the result is they will now have a charge of equal magnitude, which is -1 coulomb, -1 coulomb there. So now what happened, remember this one, we say it had an excess of electrons. So excess of electrons because it is more negative. So the more negative your electron is, or I mean the more negative your sphere is or your charge is, then that means there's excess electrons. And the more positive it is, that means there's a deficiency of electrons. So this one is the one with the deficiency. As you can see, it is more positive, meaning it has more protons. This one has excess of electrons because it is more negative, it has more electrons, right? So now what happens is when they start to come to contact, the one with an excess of electrons will donate its electrons to the one with a deficiency of electrons. Now what happens in the process of donating, the one with an excess of electrons will find itself losing electrons. So from -4 Coulomb to -1 Coulomb, that's a loss of electrons because it is becoming less negative, right? So when it's becoming less negative, that means it is losing electrons. But then this one, what about this one? It's becoming less positive. So from +2 Coulomb to -1 Coulomb, that means it's now gaining electrons, right? So it's becoming less negative and becoming more negative. That means in the process, this one with the deficiency of electrons is now gaining electrons. So that's what we say. The net charge of the electrons will remain constant in a what? In an isolated system. Because if you come to look at it, if you say -4 plus +2, that gives you -2. But again, if you say -1 plus -1, it also gives you -2. So we can say initially to finally, then the net charge of the electrons remains constant, right? So the net charge of the electrons remain constant. No charges have been lost during the physical contact, right? So let's move along. So now we had this formula in grade 10, which is Q is equals to NE, whereby we said Q is for the charge, which charge is always calculated in coulombs, so that's the SI unit, and then the number is then the N is for the number of electrons, which you can see there is no SI unit there. If you are calculating the number of electrons, let's say you have 5,000, you just say 5,000 electrons. And then the E is the charge on electrons. It is there on the formula sheet, on the data sheet. So it is given as -1.6 times 10 to the power of -19. And then you will recall that this formula, this above equation, we used it to calculate the number of excess electrons from a sphere. So if the question said calculate the number of excess electrons that are in the sphere after the sphere came to contact with another sphere, then we used to calculate using this formula. So this formula is to calculate the excess electrons, the number of excess electrons. Then the principle that we use to apply for the above formula is called the quantization of charge. Then we also had another formula, which is change in Q is equals to NE. Quite similar to that other one, but then right now we have change in Q, meaning that we have the Q finally minus the Q initially is equals to the number of electrons times the charge on electron. So the QF is the new charge of the sphere after it has came into contact. So if we go back to our example, the -1 Coulomb will be the final charge, right? So remember, initially A, we say initially A had what? -4 coulombs. But then finally it now has -1 Coulomb. So in your QF you'd substitute -1, and in your QI you'd substitute -4. So that is what is going on here. So the above formula, we used it to calculate the number of electrons transferred from one sphere to another. So if we wanted to find out how many electrons were transferred during that physical contact, then we used to apply this formula. Then the electrons are transferred from the sphere with an excess of electrons to the sphere with a deficiency of electrons. As I've stated, always electrons will move from the one that is an excess of electron to the one that is a deficiency of electrons, right? So we can always place it as the case whereby the rich will always give to the poor. poor, right? So the rich in turn will lose their money to the poor, but then the poor will gain, right? So that is the case. The rich, we can say these are the ones with then excess of electrons, and the poor are the ones with the deficiency of electrons. So the ones with excess electrons will give to the one with a deficiency of electrons, but in turn the one with an excess of electron are doing what? Are losing the what? The electrons, right? But these ones are now gaining the electrons because they are receiving, right? Then our formula here goes, so this formula is the same as this one, so you can write it like this, whereby you say Q nu is equals to Q1 plus Q2 over 2. So this is the same formula that we used in order to get the new charges of A and B. So remember, we said A had -4 and then coulombs, and then B had 2 coulombs. So we said -4 plus 2 divided by 2, and then we got the -1 coulomb, right? So this is the formula that is used to calculate the new charge on each sphere. We'll now have this above formula is used to calculate the new charge after two spheres have been brought together or released to make contact, then separated. So we say the two spheres will now have the same charges of equal magnitude, the -1 coulomb and -1 coulomb. Hence, they move away from each other after contact. So now remember, if charge A or sphere A has -1 coulomb and sphere B has -1 coulomb, what is happening now? They now have like charges. And what do we know about like charges? They repel, right? So if the charges are the same, they will repel. So here it's not only that they have equal magnitude in terms of the size, but then they also have the same signs here. You can see it's negative and negative, so they're both negatively charged, so they will repel. And then we say the new charge is the final charge of each sphere, as we have indicated that the new charge, the Q nu, is actually the QF of each sphere, right? The final charge. Then having either gained or lost electrons to each other, we know the ones that have gained is the one that initially had a deficiency of electrons, and the one that has lost electrons now is the one that initially had an excess of electrons. So this principle we say is called the conservation of charge, right? Because remember, we are not losing the total or the sum of all the charges. The sum of all the charges will remain constant, right? Okay, so let's get to the real deal. Grade 11 electrostatic. So the first thing that we need to know when it comes to grade 11 electrostatic is the Coulomb's law, right? Now the Coulomb's law states that the electrostatic force between two charges is directly proportional to the magnitude of the product of their charges and inversely proportional to the square of the distance between them. So we can see some similarity with the Newton's law of universal gravitation in terms of the definition and also in terms of the formula that is used. Remember, the formula for Newton's law of universal gravitation was G m1 m2 over r squared. Now from this one we can tell that they just only substituted the G with the K and then replaced the masses with the charges, and also the F here is not the F here. So here the F in this one is the gravitational force, but the force on the F on this one is the electrostatic force. So that's the difference between the two. So now we have F is the electrostatic force, which is given in newtons, and K becomes the Coulomb's constant, which is always substituted as 9 times 10 to the power of 9, and then Q is the charge, which is always be given in coulombs, and then R is the distance between the charges, which is always in meters, right? So a necessary conversion that you will need to know for the distances is that sometimes they will give you the distances in centimeters and millimeters. But then you must remember that to substitute into this formula here, you need to have it in meters. So now, what do you do if they give you in centimeters? To convert centimeters to meters, we know you have to divide by 100. To convert millimeters to meters, you have to divide by 1,000, right? A quick way to remember that would be this. You say King Henry died a mysterious death called measles. Now note, when you are going to the left, you need to divide, and when you are going to the right, you need to multiply. Because going to the left, you can see that you are moving from a smaller conversion scale to a bigger conversion scale. Remember, this is millimeters and this one here is kilometers. So obviously, taking a quantity from this side here, you'd have to divide in order to get it in kilometers, right? So now what are we looking for? We are looking to convert centimeters to meters. So this is what you do. You just put 1 here on centimeters and then 0, 0 up until you get to meters. So you can see that's 100. That means you divide by 100. If you want your millimeters to be converted to meters, just put 1 here and then add your zeros up until you get to meters. Then that's 1,000, right? So that means you have to divide by 1,000, because remember, you're going to the left, right? So that's it. And what are the necessary conversion for charges? Now you will know that your charges must always be given in coulombs. But in other cases, they can give you your charges in micro coulomb. So that one we say it's micro coulomb. Then this one we say it's macro coulomb. And then this one here we have nano coulomb. And the last one is pico coulomb. Right. So now if you want microcoulombs to go to coulombs, it's simple. Let's say you are given 3 microcoulomb. So you just simply replace the micro by 3 times 10 to the power of negative 3. So you replace it by times 10 to the power of negative 3. Let's say in this case here you have let's say maybe 5 macro coulomb. So that means you replace the macro by 5 by times 10 to the power of negative 6. So you have coulomb, right? So that's how you convert. And then this one, let's say you are given 7 nanocoulomb. So that means you have 7 multiplied by 10 to the power of negative 9. So you simply replace the nano here by times 10 to the power of negative 9. So this will be in coulombs. And then let's say you are given 9 picocoulomb. So this one will be 7 times 10 to the power of negative 12. But then here, you need to know the ones that are mostly common are these two, right? So your macrocoulomb and your nanocoulomb. We hardly see these ones in exam. So the ones that you need to you need to put your attention on is the macrocoulomb and the nanocoulomb. So macrocoulomb times 10 to the power of negative 6, nanocoulomb times 10 to the power of negative 9, right? Then here we have the electric field patterns. It says the electric field pattern shown in the diagram is that of a negatively charged sphere, right? So these are the electric field patterns that show us the charges of a particular sphere, right? So you will note that with the negatively charged sphere, the charges are always going inward. They flow inward, as indicated by the arrows here. If you can check these arrows, you can see that here the arrows are going inward towards the sphere, right? So towards the sphere. So always to see a negatively charged sphere, you will see by the charges flowing inward, right? Then This one, we say the electric field pattern shown in the diagram is that of a positively charged sphere. So the charges in a positively charged sphere flow outward from the sphere, as indicated by the arrows. You can see the arrows are pointing away from the sphere, right? So pointing away. So once they are coming away from the sphere, that means this is a positively charged sphere, right? So if they want you to draw electric field pattern of individual spheres, then that's how you draw those, right? Then okay, like that. Then here we have what happens now when we start to bring these spheres closer to one another, and we try to make them uh, to 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 be in contact. So this is what happens. Remember, you can either take a positive sphere and a positive sphere, or a negative sphere to a negative sphere, or a positive and a negative, right? So here we have a case whereby we have a positive and a negative, right? So we say the above figure shows the electric field pattern between spheres of unlike charges. So as you can see, that's a positive and a negative. Then we know unlike charges, they attract. So the electric field patterns of the spheres, they intersect. As you can see there, we have our spheres intersecting there, right? So we say the charges flow outward from the positively charged sphere. As you can see, we still have that. But then here there is a bending of the electric field patterns. Why? Because of that force of attraction that is taking place here. So there is that bending of the electrons that are no longer as straight as these ones. Remember, these ones, there is no force of attraction because they're just individual spheres. Then here now, these spheres are now brought together. So you can see there is that bending of the electric field patterns to show that there is a force of attraction. But then from the positive, your charges are still outward, coming away from the sphere. And then in the negative, you can see that the charges are flowing inward towards the sphere, right? So the charges flow outward from the positively charged sphere and inwards from the negatively charged sphere. Then for this one, this figure shows the electric field pattern between two negatively charged spheres. So we can see they're all negative. Why? Because we can even see with the charges they're moving inward in both the spheres, right? But then what is happening? This is a negative and a negative. The charges are the same. We say they're like charges. Now, what do we know about like charges? Like charges always repel, right? So like charges will repel, they will move away from each other. Hence you can see here they do not touch, right? So they say NB, be mindful of the shape formed due to the repulsion of charges. They do not touch. The field lines never touch since the spheres repel each other due to like charges. So you must always remember that the spheres do not charge, they do not touch, right? So that's how you will have your drawing, and also indicate the correct arrows for the charges that are going inward, since this is a negative charge. Then we have the electric field pattern for the two positively charged sphere. So the figure above shows the electric field pattern between two positively charged spheres. The charges flow outwards from each other. As you can see, the arrows are indicating that the charges are moving away from the sphere, right? Then the field lines do not touch, since these are like charges and like charges repel. So also be mindful of the shape they form due to the repulsion of charges, right? So you can see that they never touch here, right? They never touch. They form something like an asymptote. Then we have the electric field strength. What is electric field strength? We say electric field. We say the electric field at a point is the electrostatic force experienced per unit positive charge placed at that point, right? So they always ask you to define that. the electric field at a point. You say electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. Then for that one, we have the equation which is written like this: E is equals to F over Q, right? Now the Q is where we say E is the electric field strength, which is given in Newton per Coulomb, right? So in Newton per Coulomb. So you see NC to the power of -1. And then F is the electrostatic force, and then Q is the positive charge, right? So the positive charge that we are talking about there, for Q, you'll be substituting that 1.6 times 10 to the power of -19, right? Then we say this above formula is to be applied if you want to calculate the electric field strength and the electrostatic force is given. So you can see here you want to calculate the electric field strength, but then you are given what the electrostatic force. So it's just a matter of putting the value for the electrostatic force divided by Q, which is 1.6 times 10 to the power of -19, and then you will get the electrostatic force, right? Then we have now another formula for the electric field. So we say it's KQ over R squared, right? Which you can see from the one whereby we are calculating electrostatic force, we only took out 1Q, right? So that forms the formula for the electric field strength. This is the one that we mostly use in a lot of questions, whereby the electric E is for the electric field strength in Newton per Coulomb. Then K again is the Coulomb's constant, which is 9 times 10 to the power of 9. And then Q is the charge, which is given in coulombs. And R is the distance between the sphere and the point charge. Remember here, the distance is now between the sphere and the point charge that they will be talking about. Then we say this above formula is to be applied if you want to calculate the electric field strength and you are given the magnitude of charge and the distance between the charge and the positive point charge. So